Well, a very warm welcome to this 24th series of the Darwin College Lecture Series. We really have been going for a quarter of a century. And the subject this year is risk. And the whole programme has been put together by my colleagues Layla Skins and Michael Scott and Tony Cox, including the visuals, which I think you had earlier on. You'll see we've introduced the innovation of having an examination before you start, but this will not be repeated. Risk. Over the next few weeks, we're going to be concerned with how the media abuse it, with how the human mind copes with it, with how governments struggle with it, with how the classical world conceived it. We're going to be concerned with how terrorists manipulate it and how nature creates it. And then, I suppose, appropriately, we're going to end with how we ourselves increase it through climate change. But this evening, we're very appropriately starting with the question of how we, as individuals, try to quantify it. And we're very fortunate to have as our speaker David Spiegelhalter, who is the Winston Professor of Public Understanding of Risk here at Cambridge University. Professor Spiegelhalter was educated at Oxford and at University College London, and he's worked at Brunel University and Berkeley and Nottingham before coming to Cambridge to the Medical Research Council's Biostatistics Unit. He is a very distinguished statistician with a special interest in Bayesian approaches, but he's very grounded in being practical and has done work on things to do with clinical trials, expert systems, epidemiology, and ethical monitoring, and so on. However, for our purposes, one of the really important things is he's a famously good communicator. And when you get a subject such as risk, which is both hugely important but horribly elusive, that's really important. So it's a great pleasure to introduce David Spiegelhalter.
Well, welcome everybody. Well, this is quite an intimidating sight, especially as I know there's quite a lot of people not in this room watching as well. So thank you all very much for coming out on a cold evening. I'm going to talk about risk, and risk is a big subject, a very big subject. And first of all, I'd just like to give my thanks to my collaborators whose work I'm going to be showing during the talk. Now, the Winton Programme, a bit of a plug to start with. The Winton Programme, I'm sponsored by a hedge fund, Winton Capital Management, your friendly neighbourhood hedge fund. And we have a website, Understanding Uncertainty, which contains a lot of educational material. And we have a hands-on risk roadshow run by Nadia Baker. We go around schools talking to children of all ages about risk probability and what are the odds. And we're also engaged in various other collaborations, and I just wanted to give a plug to a talk next week by Mike Rawlins on Thursday on NICE, who's chair of NICE, and this is to do with, there's a whole year-long Mellon Sawyer seminar run at Crash, which is going to look at risk from all aspects, both the quantitative and from the humanities perspective. Okay, that's the end of the adverts. Risk, I looked on Google today, you Google risk today, and you find a number of risk stories, just to give an illustration of how wide a topic it is. So the first one, I like this one. This looks like the sort of thing that Ben Goldacre is going to talk about next week. So I didn't want to intrude upon his talk. But there's risk, we think about it as individual, what we might face in our lives, our medical risks. Then we see comments like Britain's now risk averse for good reasons. This is actually discussing aversions to going to war, perhaps for good reason. But we now see risk being used much more in the social context, for general feelings of a society. And then another comment which is more to do with political risk of our politician's status and how his policies might affect people's views of him. So risk is enormous. It's just so huge. And as the master described, it's going to be covered in so many aspects over the next few weeks. So what I wanted to say is, what do I mean by risk? And it's such a broad, so you can make up any so I made up a definition, because there are so many around, you might as well just make up a new one. And mine was anything to do with situations where bad or good things might happen. So it's pretty, is that good enough? Yeah, it covers just about everything, doesn't it? So, risk, take a risk, it might be a good risk. Yeah, well, I'll take a risk on it, that's all right. A good thing might happen, a bad thing might happen. So those are what I'm going to be talking about. And the point is that a lot of work in psychology has shown that we mainly use gut feelings to react to these situations where we don't know what's going to happen. And that works very well. We respond in a natural way. We're quite cautious in some situations, sometimes slightly more daring. And those situations, those responses work very well. But we know that our responses to apparent threats vary enormously according to the culture that we live in, our personal emotions, our own experiences of ourselves and the people we know. Media coverage can blow a risk up, as we all know, and our feelings of dread for particular outcomes, so that we all know that there's certain threats that really create a lot of interest and a lot of anxiety in people. Okay, and that works, actually, with all that, we manage to get by most of the time. And, people in evolutionary psychology suggest that, this reacting by, in a very sort of emotional and gut way has worked very well for us. And you could say that might be one of the reasons that, for example, probability theory was so late in being developed in our culture, not until about 350 years ago, way after most other mathematics. So, why not? That's fine then. Why do we need anything else? But the point is that gut feelings can be fine, but they can be unreliable in certain circumstances, and really you can't trust them in some circumstances. When people are trying to manipulate you, when you're not getting all the evidence, or when the reasoning is very complex to come to a conclusion. I don't know if anyone understands pensions. But I haven't got a clue. I couldn't do it. And it's generally increasingly recognized now that people, even well-informed people, are completely incapable of making a pension plan for themselves. And the other areas where a lot depends on the decision. I think we'd prefer that our government didn't just react completely from the gut and stick their finger in the air when they had to make a difficult policy decision, but they made some attempt to weigh the benefits and harms of their actions. And this weighing of potential benefits and harms is a rather unnatural thing to do, this more formal analytic approach. And it does rely on putting numbers on probabilities, actually quantifying our risk. And that's what I want to talk about, quantifying our uncertainty and putting it into decisions that we might want to make. So that's, that sort of delineates what I'm going to be talking about, and it in no way says that that's all risk is. Okay, so I want to start off with a simple example. What I'm going to do in the talk is really start off with nice, well-controlled examples about our uncertainty, where we sort of know what the uncertainties are, and then work towards much more complex, messy problems, where this is all much more difficult. So I hope you've all done your exam. If you haven't, I might have to explain the lottery. Who buys lottery? Anyone own up to buying lottery tickets? Go on, please. Yes. Good. Thank you very much. I'm glad there's somebody. For those who don't, what you do is you get your little shiny £1 coin and you go into a shop with that sign and you fill in a ticket like this, or you fill in. So I did this one. I filled in those numbers, random numbers, as you can see. That's what I fill in. So I want you to all do the same. Have you all paid your £1 and filled in your lottery ticket? Yeah, come on, if you haven't, could you do it? And could I ask my glamorous assistant to come up and help me with... Now, I'm not Dale Winton, unfortunately, but we do have a machine. This is Mike, who does all my work, all my animations for me. That's it, get rolling. That looks good. Okay. All right, so what we're going to do is... What I want to see is anyone's going to win any money. So, Mike, first ball, please. Open that up. Keep going. And the first ball is?
Number 36.
Number 36. Oh, no, I don't want to do that yet. Number 36. Can you remember these? No, we can't remember them. I can do it on here. That's fine. Number 36. Okay, number 36, right.
Number 40.
Number 40. Anyone spot a pattern yet? Number 3. Did you shake them up, mate? What's got wrong with the technology? This doesn't happen on BBC. Here we go.
What have we got? 44 and 18.
44 and 18. That's all right. Keep going. I think we need... Yeah. Number 9. 49. Okay. Now, there's about 500 people in the room, and I want to know how many people have got... Did anyone get all 6? Anyone get 5? I'm going to write down how many people I think got 3. Anyone get 4? Anyone get 3? Okay, can we count those, please? Hands right up who got 3. 1, 2, 3. Anyone over there? 4, 5, 6. Is that it? No, only 6. Is that right? No, I said 10. You should have got 10. Never mind. So I wasn't very close. So there's, in fact, you'd expect around about 10. I mean, it's not going to be exactly 10, but around about the 6, not bad. So you got 3. Essentially, if you got 3 right, you would have won £10 on the lottery. So that, out of you lot spent £500 and got 60 back. Now, this considers this is not an excellent use of your funds. Okay, so that was the answer to question 1, is that if you do, the chance of getting exactly 3 numbers right, we can calculate. And it's a basic sum, slightly more complicated than you do in most schools, probability. But just to run through it, for those who don't want to know, just close your ears. But basically, the best way to think about it, perhaps, is what's the chance that the first 3 coming out were winners for you, and the last 3 were all losers. And so the first one has to be winner, which happens with chance 6 over 49. Second one a winner, 5 out of 48. Third one a winner, 4 out of 47. Then the fourth one is a loser. There's 43 losing balls out of 46. Fifth one a loser, sixth one a loser. You multiply those together, but that's the chance of that particular order, and you have to think that, in fact, those 3 winners and 3 losers could come in any order among those 6 balls. There's 20 ways of arranging that. It turns out that you get 1 over 57 about. So that's the answer to question 1. Okay, so 1 out of 57. Now, what have we learned from that example, apart from the fact that these things are quite difficult to work out? The first is that in these simple situations, we can use reason to work out the probabilities. And if probabilities are assumed known, as in this case, we don't learn anything from history. If I put the balls back in and did it again, the probabilities would stay exactly the same. It's a very rare situation when you assume the balls, everything's exactly known. However, this is the crucial thing, any suspicion of fiddling on my part would change everything. For example, I didn't put the number 1 in there. Actually, I did. I did, but I might not have. It would have been very easy not to put number 1 in there. And all the probabilities would be slightly different. The only way you'd find out about that is by doing it again and again and again and finding out. So actually, this very simple example teaches a lot about the restrictions on being able to do these exact probabilities, when we can calculate these gambling probabilities. As soon as we get into a slightly more complex situation, these things disappear. The ability to reason about, work out the probabilities from reasoning goes in even the slightly more realistic situation. So the next situation I'd like to look at is another gambling one, essentially, trying to predict Premier League football results. Now, this is something we got involved in because we were asked by the BBC to predict the football results for the final matches in last season's Premier League. Those played on March the 24th, 2009. So this is the last matches of the season. There were about 5 teams were possible relegated. Manchester United was bound to win. And I just want to take you through an example of how you could get an idea of what the score might be for a particular match. So how can we use history in this situation to get an idea of what the probabilities are for future events? Well, I was looking at the match of Aston Villa versus Newcastle. Now, Aston Villa were above Newcastle in the league, and they had scored so far in the season 53 goals and let in 48. And that's above average goal scoring, slightly above average in terms of the number they've conceded. Newcastle had scored less than average and had let in more than average, which is why they were possible relegation. So that's the statistics we've got. How can we go from those statistics to work out the probability of Aston Villa beating Newcastle? We can do it using a fairly simple model. So this is about the simplest model you can use in this situation. What we can do is to work out the expected number of goals for each team to score. Okay, how we do this is take Aston Villa. They're playing at home. A home team scores on average 1.4 goals. Now, but they're not average. They're in fact, they are scoring slightly more than average goals on average in each match. So we can call out their attack strength and multiply that home average by 53 over 46, which is the amount that they're better than an average team in terms of scoring goals. But they're playing Newcastle, so we have to look at whether the Newcastle lets in more goals than usual. And they do. They let in 58 over 46. That proportion more goals than normal. So we can call that their defence weakness. We multiply them all up and we say Aston Villa is going to score 2 goals. Well, it's not going to, we don't know they're going to score exactly 2 goals. We would expect them to score 2 goals. We can do the same for Newcastle, go through exactly the same reasoning, and we get, in fact, 1 goal. So here's an example where we are, the expected score is 2-1. Now, of course, we're not going to say that will be the score. That just gives us an idea of what we'd expect it to be on average. Now, what does average mean? We're not going to play this match lots of times. It's not like rolling a lottery ball. But we can, from those expectations, using a simple idea of a Poisson model, we can generate probabilities for any particular score. And that's what we did. And in fact, what we can do is then illustrate those probabilities. Turns out that this is the probability in terms of 100 ways in which the match might turn out. We would expect this many to be won by Aston Villa, this many draws, and this many to be won by Newcastle. So it's an illustration of the probability of a home win, a draw, and a away win. We can order these up to see out of 100 possible matches, we can think of this as 100 possible futures. In what number will Aston Villa win, in which number there'll be a draw, and which number Newcastle will win. Now, we're going to see this representation of risk a number of times, where we turn it into a proportion of 100 cases, for example. In this one, it's slightly strange, because we can't really think of 100 matches being played. There aren't going to be 100 identical matches being played. So philosophically, we have to think of it in terms of what would be reasonable betting odds about the future. We can even scatter them around, of course, if we want to do that. Okay, when we actually did all this reasoning and worked out probabilities for every possible score, these were actually read out on, which is embarrassing, on Radio 4 on the Friday before the matches, and then compared on the Sunday, this was terrifying, about what the actual scores would be. And so, for example, we said 2-0 is the most likely score for Arsenal-Stoke, as 4-1. Now, Aston Villa-Newcastle, in fact, in our model, we used a slightly more subtle model than the one I showed there. And our most likely score was 1-0. In fact, it was almost exactly the same as the 2-1 score. But luckily, 1-0 was just our most likely. In fact, that was the final score, 1-0, Aston Villa-Newcastle. It turned out after all of this that when we did this, we got 9 out of 10 right in terms of win, draw, or lose, with 2 scores absolutely exactly. And you might think, well, that was easy, all those matches were predictable, but when Mark Lawrenson, who's the BBC expert on the sports website, did it, he only got 7 out of 10 right and only 1 exact score. So I think an away win for statistics in that case. Yeah. We did and I didn't put a penny on this. Some people at BBC did and won quite a lot of money. And so I just didn't believe it would work at all, but it did. And we're not going to do it again. But the point is that many statisticians now work in sports betting companies doing more sophisticated modeling such as this. I've shown the most basic model you can use, and people, of course, build much more and more complex models. What can we learn, though, about the football predictions? What are the ideas behind it? The crucial one is that we're using historical data to assess reasonable probabilities. We're looking at the past, making an assumption that what happened in the past is going to predict what's going to happen in the future. Quite a big assumption. And it's based on a model, a mathematical model, that we know is wrong. We know that Aston Villa and Newcastle, there will be things on that day that change the circumstances. We know that it doesn't just follow from history. So we know the model is wrong, but we're still happy to use it because it should be good enough for the purpose to assess reasonable betting odds. So we're actually making some big steps here. We're saying that these probabilities don't exist externally. They're constructed on the basis of our judgment and our knowledge and what we bring in our modeling skill. We're also saying that in this model that we build, we know it's wrong. So I'd like to this is my two philosophical points this evening that are going to run through the whole lecture. And these are guiding quotes by prominent Bayesians. The first one is by Bruno De Finetti, who wrote the book Theory of Probability. He wrote a 2-volume book that thick called Theory of Probability, whose first words are probability does not exist, which I think is wonderful. So he's actually saying, again, probability is not a property of the outside world. Now, you could argue about at the subatomic level, you could argue about that. I would say at anything other than the subatomic level, probability does not. Even those probabilities of that lottery balls, they do not exist. They're based on assumptions about the fact that I've not taken the one out. Any probability calculated is based on an assumption. And the other great quote that everyone, all statisticians, in fact everyone should have engraved, tattooed on them, is that all models are wrong, but some are useful. Every model we build is a construct. It's a mental construct. It helps our reasoning, but they are not the truth. Okay, so using history. History is not always a reliable guide. The example I often give in this is that if an event has always happened in the past, you might think it's going to happen in the future. So I could say if an event had happened 43 out of the last 43 times, you might think, oh, well, it's very likely to happen next time. And then I tell you that those 43 events were that the President of the United States was a white male. Okay, the score for white males so far, up to last November, was 43-0. However, we know that it changed to 43-1 from last November. But people didn't always think that. Now, this is a nice graph, I think. This is from InTrade, a major US betting exchange. And it represents the odds that people were placing on bets on Barack Obama being the next president and McCain being the next president for the whole year, every day for the year preceding the actual election. And you can see right at the beginning that Obama was way down at the bottom, sort of 7% chance of being the next president a year before. Pretty well what you'd expect from a 43 out of 43 odds, historical odds. And then it grew. What's quite interesting, it got above 50%, quite a long couple of months before he got the nomination, which I hadn't realized. And he was about 50, and then, by July, he was really racing away, 65, 70%. And then the start of the huge financial collapse, and in that disastrous week, as the banks collapsed and the insurance companies were seized, his ratings went down as well, until, and this is the answer to one of the questions, he got to 48%, and on the day that Lehman Brothers went bankrupt. But after that, a very strong recovery, all the way up to the election. So these were probabilities, and I would call these probabilities almost as strong as probabilities as the probabilities of the lottery machine. But they don't exist formally. There's no physical mechanism. They're just what were considered reasonable betting odds at the time, given the information available. Okay, so let's look at other areas where we have to consider risk to ourselves, and whether we can quantify that, and how we can communicate that. This is true. I went to see my family doctor, this is Lensfield Road, and as many of you of a certain age will know, when you go and see your doctor, they put you through this little computer program and tells you your chance of having a heart attack or stroke in the next 10 years. And mine is 10%. And which I thought, oh, that's not so, I did the usual psychological thing, which is think, oh, that's awful. And then he told me, oh, that's less than average for your age, and I cheered up again, which is I like to think I'm as subject to all these heuristics and gut feelings as everybody else. That's actually, some colleagues at the Institute of Public Health have done research on that, showing that people's perception of their anxiety about their own risk is cancelled out by quoting them relative to a general population. That's a well-known finding. Your absolute risk and your relative risk relative to the norms are equal and independent sources of anxiety, and they can cancel each other out. But then if I took statins, I'm not high enough to be recommended statins under the NICE guidelines. But if I did take them, it's likely that my risk would be reduced by about 30% at least if I took the tablets. So what does that mean? My risk is 10%, and I could reduce it by 30% relatively, which would bring it down to 7%. How can we represent that in a graph? Again, we can represent this in terms of 100 people like me, statins users. So there's 90 of them who in 10 years' time are not going to have a heart attack or stroke. And there's 7 of them who are going to have a heart attack or stroke anyway. And 3 of them, if they take their tablets like good boys and girls every day, will be prevented from having the heart attack or stroke. So if we order those up, change from a bar chart to an index like that, and these smileys are being increasing. I don't know anyone if you've been through QRisk. It's one of the programs that general practitioners are using. That the output actually comes out as smileys. What's interesting when they do their smileys is that QRisk scatter them around. And actually this changes the perception of the risk if you scatter things. You can't, it's not so easy to count the reds. You know, they don't look so big. It looks much worse if you block them up. So that looks much worse as a thing. Okay, so the answer to one of the other questions is that you know, in order for one person to be saved, 3 people, if 100 people take statins, 3 of them will have a heart attack or stroke prevented. So to save one of those, 33 people would have to take a heart attack or stroke. They would have to take their statins every day. So there's another question there. Okay, so these are the sort of presentations that are being used increasingly to communicate to people about what the impact of what they do is. Now, I don't know if it's worth it. Actually, I've been told recently that it might even be 4 yellows. My feeling is that if it got down to 4 yellows, I'd take the tablets. So maybe I'm going to take the tablets. We can, in fact, change, though, the representation. This represents 100 people like me. And you can say, well, they don't look like me. They aren't me. I'm one of the green ones. I'm not one of those horrible red people. Well, we have worked out a way to get around that avoidance of people to make so that they don't think. And that's to change it to personalize it a bit more and to present 100 me's in the future. So this actually says there's no avoiding this. This is not 100 people like me. This is the 100 possible futures for me. You know, I look old enough already. I didn't have to age them. So this is the work that Mike Pearson and Ian Short have been producing, where you can visualize possible futures for you. And I'm working with psychologists now on this, using this idea of possible futures as a way to really communicate the consequences of people's actions. Okay. There are other ways to represent uncertainty, and there are other things we might want to represent uncertainty about. So one of the things we've been looking at is weather. We looked at football. So let's say we wanted to represent uncertainty about weather. We might say, and this is an imaginary situation, that, well, tomorrow, we're not sure what the weather will be at this time and place, but it might be sunny, most likely to be overcast, chance of light rain, small chance of heavy rain. That's what that graphic would mean. And then we can scatter them around and say, out of 10 possible ways in which things might turn out tomorrow, these are things what might happen. Now, another idea we had was to use the tag cloud idea. Many of you will have seen these on websites, where the size of the word represents the salience, perhaps the number of times it's been used in a speech or something like that. So here, the size of the word represents the chance of the event occurring. So your eye is drawn to the most likely event. We've been dithering around whether to use the size of the word or the font size. Now, you may think these are slightly funny ideas. However, I do have to tell you that these ideas might be coming to your way faster than you think. Because what I'd like to show you now are some screenshots from the Met Office. The Met Office are investigating different ways to communicate uncertainty about future weather. They've had enough of everyone telling them off because the forecast was wrong. So if they can say a probability on everything that might happen, maybe they'll be able to escape from some of the criticism they've been getting for the last few days. So I'm not going to ask you to vote on them, but I'm going to show 4 presentations that they're trialing. And then at the end, I'll tell you how to find the website, and you can go and vote on them, see which one you like best. This is an interesting one. So here they're talking about the temperature over the next 5 days, showing what they expect the expected temperature will be, but the range, showing the uncertainty grows as you get further into the future. The temperature could be anywhere between 2 and 8. We expect it to be about 6. So you're getting a distribution of a temperature, and you could do the same with rain, wind speed, and cloud cover. Here's another one. They're using the word cloud idea. Here they're representing rain, wind, cloud, and temperature all together with the most likely forecast in the middle using bigger font and stronger font. So as the less likely events decrease in size and in the density of ink. Of course, it's not giving us precise information as the other one. Here's another one where they're using icons, again, using an icon display with the less likely icons disappearing in terms of the density of ink. So against the most likely event, the salient event. But that's a really simple summary compared with the other information. And this is the most scientific. This is one where they actually give a probability of rain and probability of snow. And the answer to the other question I set was the probability, if this is above 60%, then they issue a weather warning. It has to get above 60% for them. So that's why they get told off for not issuing weather warnings, because the probabilities were less than 60%. Now, the moment they get told off, because they're not reporting these probabilities. They are to certain customers, but not to the public. And so if you're interested in this, Google that, go onto their website, vote for it, and vote for the presentation that you want. My feeling, and from a lot of psychological work, is that no single presentation of risk suits everybody. There's a wide range of preferences. There's a huge disagreement of what people like. And it's very likely that they'll have to end up with multiple presentations. Okay. Now, soon we'll be getting on to some areas where really we find it difficult to quantify risks. But I'd like to just talk a bit about quantifying the risks of daily life. Now, you get a lot of attention for this sort of thing. This is the kind of stuff that's, these threats that are going to kill you every day. How do we measure them? How do we compare them? Well, what I sort of say, you need a friendly unit of deadly risk. It's like David Mackay has done so well in bringing everything down to single whole numbers to enable to compare sort of energy usage. And unfortunately, I didn't make it up, but the best unit is a Micromort. It's a wonderful unit. And I wish I'd made it up. It was Professor at Stanford made this up about 35 years ago. It's a 1 in a million chance of dying suddenly. So this is acute death, if you can think of, acute death. This is getting up in the morning, tiddly-pom, and not going to bed at night. Or going to bed at night dead. Now, how often does that happen? Well, amazingly, there's about 50 people each day in England and Wales are killed. Die suddenly of non-natural causes. Section 20 in the ONS codes. Out of about 50 million people. So that's a number, and this is murders, road accidents, struck by lightnings, falling down ladders, etc. Okay, so on average, we, in good health, experience a Micromort every day. So all of us, on average. Now, some people, don't spend their Micromort, and others spend a whole street's worth all in one go, depending on how they live their life. But on average, we spend one a day. And of course, as I said, averages can be very misleading. I'll tell my schoolboy joke now. Looking around this audience, I would say that people in this audience have on average 1 testicle each. Okay, so now we can see, how many Micromorts are we spending when we conduct our daily life? And in particular, we can look at transport. How far can we get per Micromort? Well, average in a car, we can ziz at least about 200 miles on a Micromort for a 1 in a million chance of dying. And it'll be more on motorways, so less on rural roads. So I got to choose every day, do I drive to work or cycle to work? Well, I could cycle to work, which is all very good for me and good for the environment. However, in terms of risk, I'm taking 10 times the risk on average, cycling than driving for the same length journey. You only get 20 miles from Micromort cycling. Now, it depends. If you're a cycle courier in London, you probably get about 300 yards. But that's, and it's made up for, all we old people pedaling around Cambridge all nice and safely. So that's on average. Now, walking is interesting because I could walk to work instead. But walking, you might guess, you might be slightly surprised, is slightly less than bike, but not much, about 16 miles. And of course, it depends where you walk and how you walk, and whether you're running out in front of cars. Now, motorbikes, I don't know how many middle-aged bikers there are here, but let's hope they stay middle-aged. Let's hope they reach their old age, because by motorbike, sadly, you only get 6 miles for a Micromort, and that's on average. So, this really is a high risk. But remember that 6 miles on a motorbike, because actually for a Micromort, it actually provides quite a useful unit when we compare, perhaps, other ways we can spend our daily Micromort. Well, we could. I mean, I'm not suggesting you go out and try all of these, by the way. This is, but just in case you wanted to. Well, the first interesting one, I think, is if you had to have an operation. And if you had to have a general anesthetic, not from the operation, but just from the general anesthetic, it's 5 micromorts. So 1 in 200,000 chance of dying from general anesthetic. So that's 5 micromorts, that's sort of, nearly a week's worth. That's 30 miles on a motorbike, 1,000 miles in a car. So not nothing. In fact, it's about equivalent to going scuba diving once. So it's not nothing at all having a general anesthetic. Or we could go hang gliding if we wanted to, and you can use up more than a week's worth there if you hurl yourself off a hill on a hang glider. And now we get to the slightly more controversial ones. Those of you who remember David Nutt and the fuss that was made about comparing ecstasy and equasy, which is the addiction to horse riding, which he got into a lot of trouble for. But from a cold risk point of view, those are very interesting things to compare, because they're both voluntary activities conducted largely by young people to have fun. We're not comparing a risk that's being, because I was reading about an anaesthetist writing about the general anesthetic risk, and he was just compared it with the risk of being murdered. And I thought, no, that's not a very good comparison. This is not a one, people don't like risks essentially that they feel they should be in control of being compared with risks they feel they're not in control of. So, but let's have a look. Now, these are quite difficult to do, the horse riding. Well, 12 people were killed falling off horses last year. 2 people were killed hang gliding last year in this country. Very roughly, I'd say, but every time you go riding, it's about half a micromort. And say that it's given, I think there's 1 million horses being ridden in the country. About that, depends. And if you take ecstasy, round about 1 micromort. So they're not, ecstasy, I think, is more dangerous than horse riding. Ecstasy while horse riding is probably extremely dangerous. So these risks are not additive in this way. But they're broadly comparable, not incomparable. Now, the interesting one, and particularly when you think that both ecstasy and heroin are Class A drugs, is that heroin, one day as a user, is that number of micromorts. So about 1% mortality per year among the heroin-using community, which is like, going hang gliding 4 times a day, every day for your life. So we're talking about, these are really serious risks that people are taking with their lives. So, okay, so this is just trying to bring things down to common units that can be compared, a common language. This has great limitations. It only deals with things that would kill you suddenly, rather than eating your, smoking cigarettes, or, your diet or behavior, which will have long-term effects, and we can compare those with using how much will shorten your life. It's not as graphic as this. Okay, but all the time now we're assuming that these risks are nicely known. And now we come to the interesting bit, or the bit where things start getting messy. And it was identified by Frank Knight, an economist, 8 years ago, that we really should try to distinguish between what he termed risk, which is sort of measurable, the things I've been doing, where you can actually, you've got a decent history, you can put numbers on things, the risk, and uncertainty, which is not susceptible to measurement in the same way. And, well, as an example, that's my daughter Rosie, who happened to be in Mexico when swine flu broke out last April. So there she is in Guadalajara in May, doesn't seem to be taking it all too seriously, and fortunately she did get back all right. But I was asked to write an article about this, so I wrote an article, with Rosie, in fact, helped me write it, in the Times, about what the risks of swine flu was. And I'm very proud of myself that I said I haven't got a clue, absolutely none. She didn't get her Tamiflu, by the way. And the risk of I haven't got a clue. So in dealing with swine flu, the government was faced with enormous scientific uncertainty. And I won't go into the details about all the aspects of the epidemic model that they were uncertain about, because now with retrospect, although we still haven't finished, we can look at some of the assumptions, some of the projections that were made, and how the decisions were made. Now, they made extensive use of mathematical models to inform the policy, with many assumptions, and those assumptions have uncertainty about them. But the planning was strongly based on what they would call precisely said were worst case scenarios. It was definitely what was suggested. And in this case, the main planning figures, the main ones, were based on 30% clinical cases. That's 30% of the population being actually ill from swine flu, not just being infected with swine flu, of which in July 2009, the projection was one out of 300 of people ill would die, which would see 65,000 deaths. This is the very top end. And September, it was reduced to 1 out of 1,000 die, by 19,000 deaths. So those were the public projections about the planning was made. Okay, this is highly precautionary. That was admitted at the time. Much lower figures were quite plausible, but that was the basis of the planning. Now, it turns out about 350 people have died. I mean, it looks like, I think I'm right in saying this year might be actually a year where there's much fewer flu deaths than normal, because people are not dying of seasonal flu. In fact, it looks like about 1 in 1,000 of clinical cases have died. It's just that they, with a rather rough estimate, the figures that came out recently said that about 1/3 of a million people, they estimated, had been clinically ill with swine flu, which is less than 1% of the population. So it looks like they got the case mortality rather right, but the number of clinical cases was strongly overestimated. We can see some of the consequences of this. We've had this National Flu Pandemic Service since July, when you could phone up and get Tamiflu just by reporting your symptoms and then collect the drug. Now, in December, the figures of people that they have from when people returning swabs shows that only about 10% have actually got swine flu. So of people getting Tamiflu, that proportion went up at other times of the year, but at the beginning and the end of the epidemic, 90% of the people taking this drug did not have swine flu. So this is mass medication of people without any medical control at all. And the question there, which I'm not going to attempt to answer, and which will be answered, I think, over, as people go over this over the coming year, is really, can we afford to be precautionary all the time? Should we be going just on expected? Should we always be planning on the top end, the worst case scenario? Should we be so precautionary all the time? It's only by putting figures, by doing the modeling, that we know that we might be being precautionary. We clearly have been in that case. We can look at other agencies that are trying to make projections into the future and make decisions on the basis of them. The Bank of England is a nice example. For years, they've been producing these fan charts where they predict, this is one that's the latest one in November last year, they predict, this is predicted inflation over the next 3 years. And this is the inflation in the past, and they project with uncertainty about what those figures will be. And they do the same for growth, and you can see that they're predicting this is recession, it's less than growth, less than zero. They're coming out of the recession in early 2010. We should be going out along here, and then we're all rather optimistic now in November 2009. Now, one of the advantages of providing these projections with the accompanying uncertainties is that you can go back and compare their projections with what actually happened. And then we see that in November 2007, they were making these projections for growth in this way. And what actually happened was this. I don't know, about down there somewhere, I think. Now, what does that mean? What do we think when we see that? Now, we're in a very different situation from lotteries and football, and even my health in the future. This is something very surprising indeed. It's not envisaged by the models that they're producing. There are some excuses around this. First thing is these are projections and not predictions. And in fact, the Department of Health in the swine flu always said these were projections rather than predictions. Now, I think this might be lost on many people, the difference between these. But I think the projections really are based on the assumption that every thing just carries on much as it has in the past, rather than anything remarkable happening. The other excuse partly is that this does not fill the entire distribution, and there is a tail going down here, but actually whether that tail was long enough for this not to be a surprise, I think is rather questionable. Okay, so what do we conclude from this? These are people with a lot of expertise, a lot of experience, trying to build models for what's going to happen. We did rather well predicting football results, but football does not suffer these sorts of surprises. But I think there are lessons about how much notice we take of models and how we treat models. And I like to think of them, people say they're maps rather than the territory. I kind of like to think of them as guidebooks, because guidebooks, when you buy a guidebook to a town you're going to visit, it might be out of date, it might just be wrong, it might be too simple, and it might be too complicated as well. It might just have too much detail. but they can still be useful. Doesn't necessarily mean we have to throw them out just because they make a few errors or they might be slightly out of date. But we have to take them with due caution. And the guidebook writer should be presenting it with due humility. So that's really, I think, a good metaphor for people who try to make models for what's going to happen. Okay, the crucial thing is that our uncertainty is more than just not being able to predict the future. We have uncertainty because, and I'm going to try to get a coin out of my pocket, for other reasons. And I just want to illustrate this other sort of uncertainty. If I flip a coin, before I flip a coin, I could say, what's the probability this is going to be heads? And I'm sure you'd all say 50%. And then I flip it and I say, what's the probability this is heads? And I think you'd have to say 50%. What's your probability that this is heads? It's 50% still. Mine isn't. Yeah, you lost. Sorry, you lost. What we've done in that is show that there's two types of uncertainty. We can have what's known as aleatory uncertainty, which essentially chance is the gross simplification, of course, because generally things are a mix. But chance, unpredictability, like the lottery. There's no way I can predict it. Not even Darren Brown can do that, predict what's going to come out of that. And then we've got epistemic uncertainty, which is due to our knowledge or ignorance. Now, from a Bayesian perspective, the thing about that drives Bayesian statistics is the belief that probability can be applied to both of those. That 50%, due to your ignorance of what the coin is, or mine or your ignorance of what the coin is just as valid a probability statement as before I flip the coin when it has a classical probability framework. And this idea of lack of knowledge and ignorance being something we can analyze and quantify and put probabilities on, I think is a really powerful idea that's been around for a long time, but it still has not been exploited sufficiently. It's not part of the sort of general discourse of risk in the way that I think it should be. So what I'd like to actually, yes, I've got time for this, quantifying your ignorance. I wanted you to do a little quiz. Have you got your bits of paper? Have you got a piece of paper and a pencil? Okay, some of you may have looked already, but if you turn the paper over, I'm going to see how ignorant, I want you to measure how ignorant you are, and see if you know how ignorant you are. Okay, so what I'm going to do is give a series of questions and ask whether you prefer A or B on the question. And then think of how confident you are with the answer. So I don't want you just say A or it's definitely A. If you think it's A and certain to be A, you can put 10, A and 10. If you think, well, don't know, A, 7, you think it's 70% confident that it's actually A. If you really don't know, just put 5, and you get, and it doesn't matter whether you put B5 or A5. 5 out of 10 means nothing at all. It means you just haven't got a clue. So you give your confidence a number 5 to 10. And then you're going to score yourself. And there's a little table there that shows you how you score yourself. And it's quite a nasty table. If you say A 10, and the answer is A, you get 25 points. Whoa, cool. If, however, you say the answer is B, in other words, you were sure it was A and you were wrong, you lose 75. So it's a real killer. This is to penalize cocky people. It's actually got a formal definition, which I'll talk about in a moment. Okay, short quiz. So the first one I'm going to ask you is, who's older, Gordon Brown or Tony Blair? This is one on the sheet. You may have finished that. So you want to guess A or B, which one you think you're most likely, and then give it a score, your confidence. If you've got no idea, put 5. If you absolutely know, put 10, somewhere in between. Okay? I'm not going to give you long for this. And the answer is, Gordon Brown is older than Tony Blair. All right, so you can score yourself on there. Anyone who's got minus 75 will have to come and see me afterwards. Okay. Easier one. Which is higher, Eiffel Tower or Canary Wharf? Give yourself A or B. All right, the answer is, have you got it? Everyone done? Everyone done? A. Eiffel Tower's high. Go on, give you 25. You should have given you some. Now, who wasn't sure enough to put 10 on that? I'm sure some people weren't. Okay, here we go. Which is bigger, Belgium or Switzerland, in terms of land area? Go on. You know. I'm not leaving you, those of you with, fancy phones, time to look it up either. B, Switzerland is bigger. Okay. Which was invented first, the radio or the telephone? Okay, answer. Have you done your confidence? How confident are you? This is B. The telephone was invented before the radio. I usually do this for 12-year-old kids, by the way. They do very well. Okay, which is bigger, Venus or Earth, in volume? Which is bigger, Venus or Earth? Now, maybe some clever clogs among you who know, is Earth, but only by about that much. You know, they're very close. Okay, finally, who died first, Jane Austen or Napoleon? A, Jane Austen, or B, Napoleon? Who died first? A, Jane Austen died first, just. Just died before Napoleon, 1817, I think. Okay, so that's the question. But you can ask it, so there's 6 questions, but you can ask these questions. I do with kids, I ask them questions about, who's got a rabbit and that sort of thing. And I've thought of one I might do, which involves about our ignorance, and I'm going to ask a question about the master. Now don't say a word. Do we think that A, the master has an iPhone, B, has not got an iPhone? So A, don't say a word. A, has he got an iPhone? I don't know, I haven't got a clue. A, has he got an iPhone? B, has he not got an iPhone? Now, let's have a little test. Who in the audience has got an iPhone? Not that many. Oh, yeah, so you might want to change your probabilities. This is not an iPhone. I'm not sure if the master is representative of the community here, but if he was, then that would strongly influence your probability in this case. So now we're going to find out the truth. Does he? No. Right, okay. No, he hasn't. Right, okay. No. Well, that's it. We're not an iPhone learning community. Okay, now I'm not going to force. Has anyone got a very large negative score? Right, because, no, there are ladies putting their hands up. Because when I do this with kids, there's a strong sex-linked ratio that the boys tend to have very large negative scores because they're all cocky and they don't know what they're talking about. Okay, I don't think I can score everybody. Has anyone got more than 100? Whoa, cool. Has anyone got less than 200? Yes, a few of you, yes, okay. So the point is, this is only a small exercise. This is the sort of exercise that you can put people through, usually in areas they know a bit more about, in order to train them to be probability assessors. Weather forecasters go through this process, other people, volcanologists go through this process. People involved in assessing using subjective judgment to make judgments about natural hazards and weather go through this process to train them to be probability assessors, to be able to be good expressors of their own ignorance. Because if you score badly at this, you don't know what you don't know. And you should know what you don't know. And that naturally leads us to this whole area, which I'd like to finish off with, which is the area of the unknown unknowns. What do we do when we don't know what we're talking about? Because when we're trying to model the future, when we're doing, modeling in any process at all, right from a lottery to climate change, we're making various aspects, various assumptions. We're talking about the probabilities, uncertainty about what actually might happen, which ball might come out. But we're also talking about the parameters in the model, for example, the probabilities of these balls. We assume they're all equally likely to come out. But maybe we're uncertain about what those are, if you thought I'd been fiddling it. We're also making some assumptions about the process by which this is being done. Are these really mixing around in this ball? Well, we assume they are, but they might not be. Our model, when we build a climate model, we're making a huge number of assumptions. We're leaving lots of things out. We know that there are alternative models. Everyone's building different models. When I build a model for football, I'm making lots of assumptions, which I know are not strictly true. However, I might think that, if I only built a bigger model, I could get it right. And that's what people in weather forecasting tend to do. However, the final business is what is this is a technical, it's not a very technical word, which I quite like a term of discrepancy, means the inevitable gap between what we as human beings can construct using our formal apparatus and what actually is the truth of the world. That gap between reality and our ability to model it using mathematics, physics, etc. And that's the interesting thing, I think, because that really deals with surprises, unknown unknowns. So, for example, then just finishing on, winding up now, this is a fascinating exercise. This is the UK Climate Impact Programme projections being made and being made for at quite a small scale. This is on a 25 kilometre square in the east of England by 2080. So, this might be Cambridge, under the high emission scenario. High emission scenario means that none of us change our behaviour. We keep on, we don't listen to Dave Mackay, we just carry on doing the same as usual, belching the stuff out into the atmosphere. And so this is if we don't take any notice at all. This is the probability distribution for the change in mean daily maximum temperature. So that you'd expect it to go up by about 6 degrees, really high, really punishing, but with a lot of uncertainty about that. Even, with a certain probability that it'll be negligible. But with certain probability, well, there'll be a massive change, devastating change in temperature. So this is controversial to actually put a probability distribution on something that is so uncertain and so many sources of uncertainty that the Climate Impact Programme is coming for a lot of criticism for this and is being criticised for it. They've really made a huge effort to allow for multiple sources of uncertainty. I can't go through all those now. I'm sure Bob Watson will be talking more about that in his talk later in the series. But they allow for the uncertainty about the parameters, they allow for the randomness, or essentially the unpredictability, the chaos. They allow for structural uncertainty about the models by running multiple models and comparing those and allowing for that distribution. However, there are certain things that they acknowledge they haven't allowed for. They haven't really allowed for the fact that all the models might be wrong. They haven't allowed for the effect of volcanoes, they haven't allowed for the fact, some other factors. So, now we come back to the patron saint of risk analysis, Donald Rumsfeld, which I hope you all got, the man who said there are also unknowns, there are things we do not know, we don't know, for which he will be remembered. I hope that's the only thing he'll be remembered for. Otherwise, deserves to sink into the obscurity he so richly deserves. But this is a wonderful quote, and very appropriate. I think the quote I use for this goes back further than this, and also further back than the black swan idea. It goes right back to Oliver Cromwell, who's the answer to the final question. Cromwell's law, who in a letter to the General Assembly of the Church of Scotland, he was appealing to them not to give battle to him, to try to restore Charles II to the throne in 1650, and he said, "Is it therefore infallibly agreeable to the word of God, all that you say? I beseech you, in the bowels of Christ, think it possible you may be mistaken." A plea for humility, a plea for an acknowledgement that you may be wrong. Now, how can we introduce that thinking, that humility, into dealing in these really complex problems with these deep uncertainties, possibly these unknown unknowns? And I haven't got an answer. I just think that this is something that we should be discussing. It should be open for discussion. We shouldn't be pretending we know more than we know. And in fact, when we're talking about uncertainty, we've got various stages, various things we can do with uncertainty. And I talk about this, I find this very difficult to speak of because I'm a chronic quantifier. I want to put everything as a probability distribution. This is where I belong. I spend my life working in this area, trying to put probabilities on everything. But there's other things we could do. Well, the really naughty thing would be completely deny uncertainty. We know it all. We absolutely are confident. And for example, in the lottery, we might absolutely be confident that this is a random process. But then might be a bit more doubtful. The probability distribution, we could just give a list of possibilities, which is what, for example, in the climate change literature they do for emission scenarios. They don't try to model human behavior as it will develop over the next 70 years. They just give a list of the possibilities and say, well, we're just going to condition on each of these. It's up to you to almost decide which one you're going to follow. We could be a bit looser than that. We could just informally acknowledge uncertainties that we haven't taken into account, that there are things that we haven't modeled. And so this happens in the Climate Impact Programme. They describe things they just have not included. They say we don't think it'll make that much difference, but we could at least informally acknowledge that our inadequacies. Or, of course, we know they're there and not tell anybody. Now, this seems to me, I don't know what's more culpable. There's two things you can do down here. First of all is to know there's things you're not taking into account and not mention it, or not to have ever even thought of it. I don't know which is worse, really. This is we'll talk as if this is the model and hope that nobody asks us any nasty questions. And this is, oh, wow, God, who would have thought it? We never even crossed our mind that this would happen. And I don't know which is worse, in effect. So the point is, all these are done at the moment. As a modeler, I would love everyone to give probabilities, but know that at these deeper uncertainties, that's really not going to be possible. we can't just put probabilities on everything. We haven't got the judgment, we haven't got the data. We haven't got the agreement about it, because a lot of these things are disputed. So to conclude, we should try and quantify our uncertainty wherever possible. But we also, and this would be my dream, would be develop a clear language to honestly communicate deeper uncertainties, so that we could do that with due scientific advisors, advisory committees, etc. Could do that with due humility, but without fear of being then just dismissed either by government or the press as being, dithering scientists. Now, and the temptation, of course, is to try to reduce everything to numerical risks and put numbers on everything. And it really hurts me to say, but I don't feel that's actually appropriate in many situations. And I think this is going to be, all I can do is recommend the remaining talks in this series, where I think people are going to be talking about much more difficult things than I've been talking about this evening. Thank you very much.
Well, the reference to that great thinker, Donald Rumsfeld, made me realise that if I've followed correctly, what he should have said is not known unknowns and unknown unknowns. He should have said aleatory probabilities, epistemic probabilities, and, of course, in his case, micromorts in large quantities as well. Another thing I got from this lovely talk was a new slant on Oliver Cromwell. His advocacy that you should know what you don't know just appeals to me. He clearly should be the patron saint of academics. We broaden the frontiers of ignorance as a profession. I was going to make a joke about lotteries being a tax on stupidity, but there's nothing at all stupid about what David has been talking about. And I think the thing that I really take home from it is this, that there are huge rewards to society if we can help people estimate risk better. And David's contribution to that is enormously important. Thank you very much.
Thank you. Thank you. Could you hand in your exam sheets at the back, please?